Numerical differentiation is the topic of the beginning of chapter 4, and we're just going to do the most basic things in here and not much beyond that. And what you need to realize is that we are trying to essentially approximate derivative values of some function based on values of the function itself. This is something that you do get in a calculus course, and let's actually approach it initially as you might get in a calculus course. Let's say the function in question is f of x equals sine of x. Of course, we know the derivative from calculus is cosine. We know the answer, and that is the common theme in many of your book problems and in the reading is that you actually know the answer. You've got some underlying formula, some analytic form of the function. All this stuff, all this theory and numerical analysis applies even if you don't know the underlying formula. But if you don't know the underlying formula, you really can't use the error bounds that you might like to use. And in theory, if your function behaves kind of wildly, the error bounds might not be of much help anyway. And so it's a little funny that way, but let's go ahead and go with it. Yes, you know the answer. F prime of x is the cosine function. And we could use the known answer to see how well the approximations do here. Let's approach it based on tabular data of values of the function f of x equals sine of x as is. So let's make a table. And let's pick nodes that are equally spaced, say starting at 0. And let's make 5 nodes at 0, 0, 0.2, 0.4, 0.6, and 0.8. So these are our nodes, x0, x1, x2, x3, and x4. What are the function values? Obviously, you're either given them or you can use your calculator, probably on a test. For sake of speed, I give you these values, but let's go ahead and compute them. Of course, sine of 0 is 0. That's easy. Make sure your calculator is in radian mode. As I always tell my calculus students, sine of 0.2 is, by the way, you should know, every math major should know, close to 0.2, because sine of x is close to x when x is close to 0. That's the first degree Taylor polynomial for the sine function. So we get something slightly less than 0.2 here. We get 0.198669330.8. Let's go ahead and approximate it to, say, that degree of accuracy. So 6 places after the decimal. Sine of 0.4 is 0.389418. A little less than 0.4. Sine of 0.6 is 0.564642. And sine of 0.8 is 0.717356. All right. Now, what would we do in a calculus course? That I will redo here to some degree with a little bit of a modification. In calculus, we teach about the derivative and we tell students that by definition, f prime at some number, I'll call it a, as I often do in calculus, is the limit as h goes to 0 of f of a plus h minus f of a divided by h, where a is any particular number that you want. We could use a different symbol. We could use an x. We could use an x sub 0 or an x sub 1 or an x sub 2. We could use one of these nodes if we preferred. And then we'd say, hey, this is the technical definition of the derivative. And as long as this limit exists, then the function is differentiable at a. F prime of a is going to be a number, and the slope of the tangent line to the graph is well defined. And then we say, well, sometimes this limit is hard to calculate. Is it possible for the sine function? Yes, though you do need to use trigonometric identities. It is a little tricky to calculate the limit. But we could also say, well, it's approximately equal to f of a plus h minus f of a divided by h when h is small, right? Close to 0, but not equal to 0 because you don't want to divide by 0. And the intuitive justification for that is, let's go ahead and draw the sine function here, or a piece of it. If a is right here, say, and h is a small positive number, then a plus h would be right there. This distance would be h. And effectively, you are, in computing this difference quotient here, you are using or computing the slope of a secant line connecting 2 points on the curve to approximate the slope of the tangent line. Okay, and we could then use that fact and these data to go ahead and try to approximate values of f prime of x for these different values of x for these different nodes. What value of h should we use? Well, probably if we're only using these data, we should use h equal to 0.2, right? Since these nodes are 0.2 apart. So I could compute here for f prime of 0, I could compute, I'm not writing anything down yet, notice. I could compute this difference quotient as f of 0.2 minus f of 0 divided by 0.2. At x1 equals 0.2, I could compute, listen carefully, f of 0.4 minus f of 0.2 divided by 0.2, etc. And I could certainly do that, and I might very well do that in a calculus class. But there's a better approach, especially for the middle nodes. And that is to use, instead of this secant line, use another secant line. Go to a minus h as well, instead of just a plus h. And figure out the slope of the secant line connecting those 2 points. On either side of a, equally spaced from a. And you can see visually, at least, if your function's well behaved, it looks like the slope of that secant line for any given value of h is going to be a better approximation to the slope of the tangent line. Make sense? You could also go back up here and say that this is approximately the slope of this secant line. But the slope of that secant line is f of a plus h minus f of a minus h, not divided by h, but by 2h, right? Rise over run in this picture for this bigger triangle here. The run is not h, the run is 2h. And it's probably a better approximation for any fixed small value of h. Does that make sense? So at least for the middle nodes, where we can use nodes that come before them, we probably get a better approximation this way. Now let's go ahead and do that. So like at 0.2, we could compute not f of 0.2, but f of 0.4 minus f of 0.2, f of 0, divided by 2 times 0.2 divided by 0.4. At this one, we could compute f of 0.6 minus f of 0.2 divided by 0.4. And at this one, we could compute f of 0.8 minus f of 0.4 divided by 0.4. I'm using h equal to 0.2. I'm dividing by 0.4 because I'm multiplying h by 2. I'm using this approximation, not the other one. You can see again visually, it's probably a better approximation. It's probably a better way to go. So let's go ahead and do that now. So with this first one, Well, okay, I'm subtracting f of 0, so which is 0, so that makes this first one a little easier. I'm just going to do 0.389418, 0.389418 minus 0 divided by 0.4, 0.973545. The next one, f of 0.6, you can see is 0.564642. Right, track with me here. Be looking up at the screen maybe instead of writing something down right at the moment. Taking this number, that's f of 0.6 minus f of 0.2, this number, 0.198669. Divide that by 0.4. This is about 0.914933. Please let me know if you see any mistakes that I made. At 0.6, f prime of 0.6 would be approximately this, which will be 0.717356 minus 0.389418 divided by 0.4. Divide that by 0.4, and you get about 0.819845. How good are these? Well, we know what the answer is. F prime of x is cosine of x. So for example, cosine of 0.2, we hope is not too far from 0.97. Is it? Cosine of 0.2 is 0.98. If instead we had just used h equals 0.2 and used this kind of approximation, would we have been further off? Let's see. I could have also done f of 0.4 minus f of 0.2 divided by 0.2. Catch that? Right here, I also could have done f of 0.4 minus f of 0.2 divided by 0.2, again, using this idea. Let's do that and see if it's worse. I'm hoping it's worse. I'm hoping this is better. So f of 0.4, 0.389418 minus 0.198669 divide by 0.2 instead of 0.4, 0.95. Yeah, that's worse. Right? The true correct answer is cosine of 0.2, 0.98. This difference quotient gave us about 0.97. The other one, when we use this with some h equal to 0.2, is a little worse. It was about 0.95. This is a better approach. Visually, this secant line approximates the slope of the tangent line better than this secant line does. But what do we do at the endpoint nodes? 0 and 0.8. We don't have function values before 0 or after 0.8. Well, that's a little bit of a lie because, well, we've got a calculator. So we could figure those values out, like, sine of negative 0.2 and sine of 1 could be figured out, and you could add to your table. But that's cheating, right? We just want to use the tabular data that we're given. So what do? Well, we could compromise and say, okay, let's go back to using this formula. At 0, when h is 0.2, and at 0.8, maybe we'd have to use a negative value of h to use x3 equals 0.6 instead. Use a slope of this secant line instead. We could do that. We could use h as negative 0.2 and still use this formula if we wanted to. And it would give still a slope. If effectively you'd have a ratio of two negative numbers there, giving you a positive answer. But according to the book, there's a better approach. We're jumping to the punchline here of the derivation in the first 5 or 6 pages of section 4.1. I guess the first 4 pages. On page 175, there are 2 formulas. For those middle nodes, we used the 3-point midpoint formula, not the error part of it. not the error term, but this part, we essentially did f of x0 plus h minus f of x0 minus h divided by 2h. H was 0.2. X0 in this formula was not literally the x0 in the table. It was first x1, then x2, then x3. That's what we did right there. And what the 3-point endpoint formula is saying is use this formula instead. What a crazy formula. Again, we'll ignore the error term. Focus on the approximation. That's kind of a crazy formula, but according to the book's derivation, it should do a better job. Yeah. So I'm just going to write it down. It's mysterious. It's not clear where it comes from geometrically, but the 3-point endpoint formula would say f prime of x0, where it could really be x1 or x2 or x3 or x4 as well, is approximated as -3 f of x0 plus 4 f of x0 plus h minus f of x0 plus 2h, all divided by 2h. What a crazy formula. So for example, f prime of 0 would be approximately -3 f of 0 plus 4 f of the next node, 0.2, minus f of the next node, 0.4, all divided by 2 times 0.2. And according to the book's derivation, not really emphasized this way, but the authors, this should be hopefully a better approximation to the true derivative at 0. Now, actually, the true derivative at 0 is cosine of 0, which is 1. So hopefully, this is a pretty good approximation to the number 1. Based on the tabular data that we have, which I'll write down here, this is -3, f of 0 is 0. 4 times f of 0.2 is 0.198669, and then f of 0.4 is 0.389418 divided by 0.4. Boy, I hope this does okay. Let's see what happens here. So we got, well, that's 0. 4 times 0.198669 minus 0.389418 divide by 0.4. Yes, very close to 1. Approximately 1.013145. The true answer is 1. We can also use it at the other endpoint. This was at 0, the left endpoint of the entire interval from 0 to 0.8. We could also use this 3-point endpoint formula to approximate f prime of 0.8. However, to do so, if we're going to use the tabular data, 0.8 is the right endpoint. We'd have to use a negative value of h, so we can use, so that these numbers are smaller than x, the x0 that I'm plugging in, which is really x4 here. Now we're going to use h is -0.2. 0.8 is really x4, but in this formula, it's going to play the role of x0. So I get -3 f of 0.8 plus 4 f of x0 plus h. If x0 is 0.8 and h is -0.2, that's going to be f of 0.6 minus f of x0 plus 2h. Again, if 0.8 is playing the role of x0 and h is -0.2, this is going to be 0.8 minus 0.4, which is 0.4. So I'm going backwards here. H is negative. I'm using points to the left of 0.8. Divided by 2 times h, again, h is -0.2. The true answer is cosine of 0.8, so we're hoping we get an answer close to 0.6967 here. I'll plug in the numbers here, so we get f of 0.8 in the table is 0.717356. F of 0.6 is 0.564642. And f of 0.4, I'm looking at the table, is 0.389418. We're going to divide that by negative 0.4. And again, hopefully get an answer close to positive 0.6967 in the end. Let's see if we do. We have negative 3 times 0.717356 plus 4 times 0.564642 minus 0.389418. Hopefully no mistakes. Divide by negative 0.4. Okay, not as close as you might hope, but I guess it's in the ballpark. 0.707295. Again, that's supposed to be approximating cosine of 0.8. Okay, it's not too far. If you were asked to find the error as always is actual minus approximation, so I could take cosine of 0.8 and subtract 0.707295. The error in this approximation is on the order of negative 0.01. I guess for this small list of data and this value of h, I guess that's not too bad. It's the absolute error is close to 0.01. Okay, so it's a weird formula, the 3-point endpoint formula. No real geometric intuition for it, but you can use it. Okay. Is it worthwhile trying to study the derivation of this? I do think it is worth your while if you haven't yet. I think I do want to take a little time to look at it together and encourage you to study it in more depth on your own and for your personal edification. And if nothing else, to also review Lagrange interpolation, which I will remind you of as part of our review for the exam as well, if you're not. And to appreciate that the error formulas can arise from this, which are part of the formulas that are in the book, those error terms. And that's a worthwhile thing to know. In numerical analysis, is always worthwhile to know about error terms. So let's just take, hopefully, 5 minutes to briefly look over the derivation of this. Can't completely understand it in depth in 5 minutes, but I want to maybe in 5 minutes help you believe you could, with enough effort, understand it. So what's the idea? We're trying to obtain general derivative approximation formulas in the same kind of setting as always. We've got n+1 nodes. For a Lagrange interpolating polynomial, that means the degree would be at most n, and usually exactly n. There are your nodes, labeled in the usual way. Some interval where the function is nice, n+1 times continuously differentiable. Why do you need to assume that? So that you can say this is true. That's why you need to assume that. So you can write that n plus first derivative and say there's some number xi of x in the interval where this equality is true. Okay, there's your approximation based on the LKs being the Lagrange interpolating polynomials, which you may have forgotten by now. I will remind you what they are. There's your error term. What is xi of x? In general, you don't know what it is. You just know it exists. Though sometimes in certain situations, you can actually solve for it. And we did do that one day. I don't remember if it was before spring break or it must have been after spring break. Maybe the week after spring break. We solved for xi of x in some examples. Although I think that was just for the Taylor polynomials. It's similar to Taylor's theorem. That's another key thing to realize is this is a similar kind of equation as Taylor polynomial equations, approximation plus error term. And the error term involves factorials and n plus first derivatives and products of differences. That's the way they run. So what's the goal here? The goal is to try to now use that formula to approximate f prime. So you differentiate both sides and get this complicated thing. This part's easy. The f of xk's, the xk's are fixed nodes, not variables. Those are constants. The lk is a function of a variable x. That's just the linearity of a derivative operator there. You're just taking a derivative of a linear combination, and you get the corresponding linear combination of the derivatives. These two parts don't look so nice, though. Where do those come from? Both of these expressions involve x, and you're multiplying them. Product rule for derivatives. Got a first function and a second function, or if you prefer, a left function and a right function. I only recently, through a 3 blue 1 brown video, realized you could say this. This is right d left plus left d right. Product rule. I always said the derivative of the first times the second plus the first function times the derivative of the second. Much faster to say right d left plus left d right. Product rule. Okay, it's a step. I guess we'd have to simplify these things. And so take the derivative of that, you need the product rule again. Take the derivative of this, I guess you'd need the chain rule, although you'd probably need to assume f has got another derivative, which I don't know that the textbook says that. Sounds like a nightmare. What they say is, if x is one of the xj's, one of the nodes, then the term multiplying this derivative is 0. I don't even have to bother differentiating that. That's a 0. And the formula simplifies to just the first part. And I guess this all simplifies to that. Is that obvious? That doesn't seem so obvious. That doesn't seem so obvious. Evidently, this derivative simplifies to this product. Does that make sense? I did, to tell you the truth, I didn't think about it ahead of time. I wonder if they're imagining, I mean, I can see the n plus 1 factorial being factored out. By the way, there's a little typo there that factorial should be outside the parentheses. But how does that product become that when you differentiate it? I think I gotta leave that a mystery at the moment and not worry about it. That's okay. That's a mystery in my mind at the moment. Maybe it's fairly easy to figure out, but let's not worry about it at the moment and try to just spend 2 minutes with the rest of it here. So this is the general n plus 1 point formula to approximate f prime of xj, xj being one of the nodes, or any of the nodes. J could be 0 through n. Notice in this product, k goes from 0 to n, but k does not equal j. I guess that's related to the Lagrange interpolation formulas. You sometimes have to exclude x minus xj. We will review that here. And actually, we can review it now in the case where there's 3 points, x0, x1, and x2. 3 nodes. Oh, okay. Now we can review. This is a little review for the exam right now. The Lagrange interpolating polynomials, when you have 3 points, 3 nodes, x0, x1, x2. Recall this is L0. If you have 3 nodes, in generally, your interpolating polynomial for those 3 nodes is going to be a quadratic. What was the method back in the beginning of chapter 3? Come up with these L functions that are not the final answers. They just help you get to the final answers. And their benefit was that you could get to the final answer without actually solving a big system of linear equations. linear algebra. That was their benefit, really. I mean, we did solve it with linear algebra as well. We solved for the coefficients of the quadratic with linear algebra. But the benefit of Lagrange interpolating polynomials, especially when you got more than 3 nodes, is you can try to solve for the interpolating polynomial without linear algebra. That's a nice benefit, I think, in general. But the idea here is L0 is going to be 1 at x0 and 0 at the other nodes. Yeah. If x is x1 or x2, this is 0. If x is x0, everything cancels to a 1, right? X0 minus x1 cancels with that x0 minus x1, and x0 minus x2 cancels with this one to give you 1s. This has a value of 1 at x0. Similar formulas arise with L2 and L1 and L2. L1 of x, when you've got 3 nodes, x0, x1, and x2, those are your nodes. You want this to be 1 at the middle node, x1, and 0 at the outside nodes. It needs to be x minus x0 times x minus x2. That'll be the numerator to make it 0 at x0 and x2. And divide by something that makes it equal to 1 when x equals x1, right? So you need to do the same kind of products except replace x with x1. This is review for the exam right now, in the context of studying the beginning of chapter 4. And the L2 of x, you want to be 1 when x equals x2 and 0 at x0 and x1. So x minus x0 and x minus x1 need to be in the numerator to make it 0 at x0 and x1. And to make it 1 when x equals x2, you need this on the bottom. And then your final interpolating polynomial based on those nodes, you could call it P2 of x because it'll probably be quadratic, would be f of x0, L0 of x, where L0 of x I didn't write down here, it was in the book, plus f of x1 times L1 of x plus f of x2 times L2 of x. This is something you should be able to do for the exam. Is simplify this in a given situation, or find it and then simplify it to get the Lagrange interpolating polynomial. That's finding the polynomial. Neville's method is more focused on not finding the polynomial, but finding approximations, numerical values of different Lagrange interpolating polynomials. Divided differences, the forward difference formula does find the appropriate coefficients and plugs the numbers into the interpolating polynomial. They're all still the Lagrange interpolating polynomial, but thought about from different perspectives. That's partially a quick conceptual review as well. Anyway, coming back to this derivation, I guess this is taking longer than 2 minutes, but we're reviewing two at the same time. We need the derivatives of those L's. So you differentiate it. Is this the obvious derivative of that? You got to do a little work, just expand the numerator. The denominators are constant, so it just stays there. Expand that numerator, FOIL it out. X squared would be differentiated to 2x. The x term would come from the outside and inside products, a negative x1 minus x and a negative x2 minus, negative x2 times x, x1 times x and x2 times x. With a negative sign, you differentiate those, you get minus x1 and the minus x2. Constant term is x1 times x2, that differentiates to 0. Yeah, that's a derivative of it. Similarly, you get these formulas for the derivatives of L1 and L2, and then you plug it all in. And then to derive the 3-point formulas that we used 15 minutes ago, you simplify to the case where your nodes are just x0, x1, and x2. and you assume they're equally spaced by h. So x1 is this and x2 is that. And then you just plug in and simplify. And you get these kinds of expressions, which become the formulas that we used 15, 20 minutes ago. Okay, so they are derived using Lagrange interpolating polynomials. And next week, when we do a little numerical integration, 1 week from now, once again, Lagrange interpolating polynomials are used to derive formulas. And error terms are involved as well. And we're not taking the time to study these error terms, or we easily could. It's nice to have them. The absolute error in each case is going to be bounded by h squared divided by either 3 or 6, depending on which formula you use, times a third derivative value. And again, as usual, even though you don't know what the c's are, if you got a formula for f, like the sine function, you could easily find its third derivative and bound it. And in fact, it's got to be a cosine or a sine, plus or minus. You can bound these derivatives by 1, no matter what the interval is. And then you could use the error terms to figure out how small h should be, for example, to guarantee your derivative approximations are within a certain error tolerance, like 0.01 or something. Not taking the time for that, but it's something we could easily do. And that would be really more numerical analysis. Well, we will do that with the integrals. 1 week from now, we will use those error terms. But here I'm just trying to briefly introduce numerical differentiation based on data as another illustration of numerical analysis thinking, you might call it. Again, it feels funny because we already know the answer. F prime of x is cosine of x, so why bother? Okay. It is still true even if you don't know a formula for f prime. Still gives you approximate values. And if you have reason, even if you don't know the underlying formula, if you have good reason to believe the underlying function is well behaved, doesn't do anything too wild, then you should feel like your approximations are still pretty good, even if you only have data. But again, the midpoint formula is great. The endpoint formula is weird, but be able to use it anyway, and including on Thursday's exam. Not the error terms, but be able to do the approximations.